So what I'm going to present is the, how do we teach performance modeling at OSU? How do we incorporate like the different instruction technology, and how do we teach software? So this is really joint work with my two TAs. I have two excellent TAs, Priya Natarajan and Nanshan. They're both in the audience, and I will invite them later to speak a little bit about their experience as well. So the outline is we will first briefly cover like what do we teach, what are the courses we teach at OSU on performance modeling, and then I will go over the, in my lectures what instructional technology I use, and then Priya and Nanshan will, talk briefly about how their experiences in teaching software, related to performance modeling. And so first, everyone in the audience, probably quite experienced in teaching performance modeling. Nowadays, around the world, we have, really a lot of different performance modeling courses in, computer science and OR, in many computer science and OR departments. So when I first was, asked to give a talk and looked at the literature, in fact, I see recent years we have an increasing trend of people sharing, their performance modeling, education. So for example, Victoria did an excellent job. She gave a comprehensive survey about, what are the performance modeling courses, during the last decade, offered around the world. And that was a very nice, overview and survey. And Dr. Tay also shared his experience on how he teaches, performance modeling, especially this analytical kind of courses. And so nowadays, when we think about teaching performance modeling, not only we need to incorporate the new topics, now, artificial intelligence, machine learning is booming. We have big data, cyber, and also all kinds of crises, economic, health, and information, pandemic, all this. And unfortunately, the rest of speakers have covered different aspects. Today, my focus is going to be on how do we incorporate, this different digital technologies in our teaching, because nowadays we really cannot kind of, ask our students to stay away from these technologies. So that's really the purpose today. We want to, also maybe with our experience, and I hope everyone can share your experiences as well. So first, what do we teach at OSU? We teach, these are the three courses basically, in my teaching load. For undergrad, we teach a course, previously was called performance modeling and simulation, recently changed to be stochastic modeling and simulation. So here, this is a 4-credit unit course. We have normally, 70 to 100 students. It's a large class. And at graduate level, we teach, a master level and then PhD level courses. The 6300 is titled Simulation for System Analytics and Decision Making. And then the 7300, it's the stochastic processes. We, for example, Moore has an excellent textbook, and I frequently use it as a reference book. And for graduate level courses, the class size is smaller, like master level, we have about 40 students, and the PhD level is often, in between 10 to 20, like that's even smaller. So those are the courses we taught at OSU. Next slide, please, Priya. So to just share you briefly, like for undergrad course, like what do we cover? We will cover, like, we want the student understand, the importance of uncertainty modeling. And then we will cover briefly like a queuing theory and help them understand what's the benefit of queuing, knowledge of queuing theory. And also we cover simulation a lot. For example, we'll teach the students how to build a simple simulation model, using either spreadsheets, or later in the lab, they're going to learn how to build a simulation model, how to simulate a queuing system, using software. Currently we use Arena, and also we are, going to switch maybe in the future, like more recent software such as CMU, etc. So another thing is basically we require our student to do a project. The project is really how we're going to tie the student to the state of art of practices. For example, we had all kinds of interesting projects students can simulate. Last year we had students simulate, build a simulation model for the whole like COVID vaccine system, because right now at OSU we have a large scale, vaccine, and we also have students simulate Amazon, the warehouses and inventory system, and also maybe other, systems. Yeah. So that's how we tie the student to the state of art. But today we're going to share more about how do we incorporate technology. So in my lectures, I use frequently three things to teach performance modeling. One is live demo, the other one is polling, and also we do games. For undergrad students, they really loved Kahoot games because this, especially in the last 2 years during the pandemic, how do we engage students? Really, students find Kahoot is really very fun, and then they keep asking, hey, when are you going to do the next Kahoot? Okay, so next, yeah. So I found the live demoing. Thanks to the technology. Like I think teaching performance modeling is so handy using, demos. For example, when I teach uncertainty modeling, when I teach Monte Carlo simulation, I do a lot of like spreadsheet simulation. And when we teach queuing concepts, we do like a live demo, using the Arena software to help students observe a queue evolution, etc. Yeah. Next, please. So I'm going to first demonstrate, like, see how do we teach, the Monte Carlo simulation using spreadsheets. So here the concept is we want to help students quickly develop a simulation model in class, and then they can, I do actually a live simulation in front of students. We, then guide the students to observe like the uncertainty, the output input kind of, relationship, and also kind of for decision making. So I'm going to just to demonstrate quickly. This is one of the very first example I show the students. So this is, let's try to help Rupert to sell the newspaper. So it's a classical news vendor problem. So here, like a Rupert every morning, he sells a newspaper at $1 per copy, but then he need to buy that first. It costs him 80 cents per copy. But then every morning he need to face a decision how many newspapers he need to buy to start the day. But then really depends on the demand. Suppose we have the historical knowledge that demand is uniformly distributed, say from 1500 to 2500. So it's a uniform, anywhere from 1500 to 2500. The question we want to ask the students, hey, now how many copies do you think Rupert should buy every morning? The classical approach or common kind of a pitfall approach is let's just do some analysis. Let's understand what's the expected demand. So it's a uniform from 1000 to 1500 to 2500. You know what I mean? Is 2000. So quickly you see, okay, now since the expected demand is 2000, you do kind of a quick reasoning. Okay, now I should plan based on the demand, based on the expected demand. So now suppose Rupert is going to order, every morning exactly 2000 copies since he expects the demand is 2000. So then you can quickly do the following reasoning. Okay, now every copy costs him, 80 cents. So he's going to put an investment up in front at 1600. Now, suppose he sells 2000, per dollar, each copy costs $1. He's going to make, a revenue 2000. So therefore, we expect his profit is 400. So this is a common approach. It's used a lot in practice. People basically plan everything based on expectation. But then we're going to then show the students, this is a problem. You cannot simply, because the reality is, let's understand what's the reality. So we're going to do this, very quick kind of reasoning about, hey, what's the profit? Profit is really a response to the demand. Okay, well, the demand is actually not, it's, you ordered 2000 copy, but then, when you do a demand, when the demand realizes, and then what you can sell is you can sell at the most 2000. If the demand is less, you end up only selling, that's based on the demand. So we can quickly develop the relationship between, profit is a function of, main demand and versus 2000, your order quantity, and then minus your investment up front. Then we're going to develop this spreadsheet simulation. So now let's think about demand. Demand changes, from day to day. So basically, demand is a uniform distribution. So we're going to do a random between, from 1500 to 2500. So then let's say, okay, we're going to quickly implement this in front of the students. If they want the demand, say it's a random draw from that uniform distribution. Suppose they want the demand is, 2000, 333, and then basically now how many you can sell, what's your revenue, what's your profit. So we're going to do this, we're going to quickly generate day 1, day 2, day 3, or maybe day 100. And then we're going to plot that in front of students, and we're going to plot the daily profit. So basically, this live demo kind of clearly helps students visualize. First, demand varies from day to day. It's really a random sample from that distribution, uniform distribution. And the profit, it's really not a linear, function of the demand. Because there's a mean in front of it. So now you can see people quickly through this plot. Once you simulate 100 days, you see, like, although in the beginning we said we expect every day the profit should be 400, but now if you look at the chart, actually the maximum profit you can get is 400. So now if you look at the average profit, of this 100 sample you get, it's actually, way below 400. So now basically through this quick demo, we can quickly help students really understand demand is uncertain, output is also uncertain. It's really not, the real world is really not a simple function of the expectation. It's not, the profit's not simply, it's a linear function of the expected demand. So, and then furthermore, we can help students understand a lot of concepts related to like simulation, for example. So all these performance metrics are really kind of, they're sample dependent. You can think, if when we want to teach central limit theorem, we're going to help them understand, everything is sample dependent, even the confidence interval, lower band, upper band, it's really depends on the sample. We can think from the simulation theory, they're just really random variables, it's sample dependent. So now here, Priya is running, a quick kind of live demo to see like when we change it, when we do a different, generate a new sample, you see like, every time when you do a different sample, all these things changes, the mean profit, mean standard deviation, the upper and the lower band of the confidence interval, they all change. And this is the way we use a live demo to tell the students, so when you're facing kind of uncertainty, output is also uncertain. It reacts to input, and then your estimation, everything, you need to incorporate uncertainty to do the correct, decision making. So here we see like through live demo using spreadsheets, it is really convenient because spreadsheets has random number generator encoded, and we also have this live function. Every time any cell changes, all the samples are reproduced, and you can also instantly show the students output. It's also uncertain. It responds, react to the uncertainty input. And furthermore, we kind of, through the live demo, we kind of teach students, hey, now, what is Monte Carlo simulation? It's really not an analytical approach kind of to tell you what's the exact answer. It is really a statistical approach to help you to kind of draw sample to get, statistical estimation about the performance. And so therefore, it's sample dependent. So we see, it's very easy to teach them, hey, all this standard deviation, mean, and the confidence interval, when they're sample dependent, we can view them as random variables. Then we can teach them central limit theorem. And further, we can teach as sample size increases. Fortunately, with this central limit theorem, we have convergence. We can eventually lead to, although every time you simulate the solution, the answer changes, but based on central limit theorem, we're going to eventually get the right answer. So those are the things, clearly, easily developed, or enabled by the demo. So what Priya is going to run for me now is another kind of live demo for queuing system. So here's a really, again, the very first model we show students. Priya is going to run a quick demo for like MM1 queue. So here you see like it's a simple drilling. So some, parts arrive, and then they need to get into the queue, and then they're going to be drilled, or processed by the drilling machine and then depart. It's a very simple system. We're going to have the students, observe what's going on, here, and we also plot on the chart, the average queue length and the average waiting time, etc. So basically, we can have students watch the system in slow motion and have them observe, observe like, how the clock advanced, why we can simulate the system, quickly. So here we can have them observe the clock. The students will observe the clock. It doesn't really tick as the regular clock in real world. Really, it's really the concept of discrete event. And further, we can ask the students, hey, now think on the spot. Now, how can you improve the performance? So we can do a lot of what if, right in front of the students. For example, we can ask, hey, what if now the...
Sorry, the video got...
So this one is basically, what if we make the processing speed faster? And the other one is basically,
this
what
one
if
is...
the arrival... Yes?
Yeah, so this first scenario is, what if the arrival rate is faster? How does this change the queue length? So this is the instantaneous number in queue, and then the red line is the average number in queue. And here, this is the average wait time from this system. So you can see by increasing the arrival rate, how this affects the evolution of the queue. And then the last scenario that we have is, what if the process time it takes less processing time? So we speed up the processing time. We see that the queue length is much shorter. The average queue lengths are much shorter. Also, the wait time is a little less.
So I see there is a comment from the chat box. Let's see. The first two examples are saturated. No, actually, I see. Let's see. Yeah, excellent point. The first two scenario, the row is, row equals 1, and the second arrival, yes. Excellent point. Thank you, Andre. We did, we did create this video last minute, so yeah, apologize for that. But indeed, yes, we will have students observe different scenarios and then go through, like, some basic concepts. Thank you, Andre, for pointing that out. And then we would first, ask students to think on the spot, what matters to the performance, and how can we improve the performance. And basically through live demo, we can basically, easily make our life easier to, have those concepts, kind of going through. So here, you see like the benefits of live demo. We have the students, see systems in action, and then it can help us to engage the students and think maybe in a more active way, how can we change the performance? How can we influence the performance? How can we improve it? Yeah. So, and the technology also enable us to really direct the attention to, where it's needed. For example, through slow motion, that can help students to understand how the clock is advanced, what's the principle behind, simulation software. And those are the things we can already mentioned. So, so live demo to me is always very handy. Yeah. So another technique I won't spend too much time is in-class polling, because it looks like Chi-Wei already covered quite a bit on, polling. Polling is another technique I find very useful to quickly assess students' knowledge. Because with the help of technology, we can easily pose a question and have students quickly, click the answer, and then the technology would enable us to see like the statistics, and and then we learn how students, have learned. So basically, that instant feedback enables students to quickly assess whether they have the right answer. Also enable this instructor to, understand, what percent of students already, learned, have the correct knowledge. So those are the things very handy. Next slide. I think I will skip through since we, really drag. So what I'm going to do next is the Kahoot game. Kahoot is another another technology I really adopted for my undergrad class. In the beginning, when I actually played the Kahoot in my graduate class, students say, "Hey, now we're graduate class. What do you think? Are we kindergarteners?" But then actually during the pandemic, I explored a few Kahoot games. Even graduate students find it's very entertaining and also very engaging, because it's very hard to have students sit behind the screen, for whole 1 hour, or even actually for my PhD student or master student, some lectures can be long, like 2 hours. So I use the Kahoot actually to wake them up, because we can make the students to get into a competitive mode. They really need to pay close attention in order to kind of be a winner about the game. Because yeah, so and Kahoot, I don't know whether maybe some of you have already learned. So in general, this kind of a game based teaching method has been kind of studied by scholars, and in general, it's reported that once you create a more enjoyable and more engaging learning experience, and in general, the impact can be very positive. For example, right now, Kahoot is really a widely adopted teaching platform. Monthly, it's reported that monthly we have 70 million active users in teaching. It's used from elementary school to colleges, and so it enables you to create some quiz and to have the user play and then compete. Because not only you need to get the correct answer, you need to be fast. So that's really wake up the students, because it's really much more fun instead of just simply listen and then come for the whole 1 hour. And the other thing is like the option of having the students playing anonymously will make some students, especially those less confident students, still kind of participate. I encourage students to use their real names, but then if you don't feel comfortable, you can use a fake name. In fact, we end up having students, just using all the faculty's names. You'll find like, Professor say Xia did a really lousy, but they have a lot of joy kind of, choosing names, but then also a lot of joy kind of winning the game. So basically that's the part to make the class much more entertaining. And also give the instructor kind of, a way to entertain or to assess the students. So here I have a quick example. For example, when I teach Poisson processes, there's some key knowledge points. For example, here we know Poisson processes, the interval times are IID exponentially distributed. But then there are a lot of misunderstandings. So here I typically design the question to kind of focus on what's important, what are the common pitfalls. For example, here, one question would be, if you consider Poisson process, with this arrival rate, suppose the last call arrived 5 minutes ago, when do you think the next call will arrive? And then we launch a game and would have the student answer, is it going to be, 6 minutes, 1 minute, a random time of exponentially distributed random time with mean 1 minute, or random time with mean exponential 6 minutes. So basically, with this kind of question, students who really understand the concept, you need to them really digest this key knowledge point to get the correct answer. But meanwhile, the good students will get the answer correctly. Then, the student who didn't understand, but through the playing the game, they will get the question. Yeah. So let's see. Maybe we will. Yeah. Let's see. So one comment I want to say is that when we design the question, as instructors, we really need to think carefully, what's the purpose, what's the learning goal of those questions. It can be, so here I borrowed from this reference, Parada, 2018, who gave some tips about how should design some, a high quality multiple choices questions to really maximize the learning goal. For example, you shouldn't really have too many answers, avoid some tricky questions, and then use simple formats and make it challenging, but not too difficult. And then you always follow up with feedback. Priya, what do you want to add on? Do we have time to?
I don't think we have time to play a Kahoot game, but I think that if there are any instructors that are not familiar with it, I think it's actually probably the most fun that the students have in the class is playing the Kahoot games. So I encourage you to go at least to the website. This is the website to play the game. But if you go to kahoot.com, you can see the website to create a game. I think it's
That's right.
if you haven't used it, it's very useful. And the students find it very fun. They have they get very competitive to see who can beat each other in the game. There's a podium, so you can see who's first, who's second, who's third. They really have a lot of fun with this. with
So
this
the other thing we do is actually, I always tell the students, not only accuracy, but also, speed. But then at the end of the semester, we actually use all the Kahoot results to give incentive bonuses to students who did really well in both, especially in accuracy. So yeah, those are the things we really made the undergrad and also graduate teaching more fun. Yeah. So what's next is we're going to talk about, I'm going to have Priya and Nanshan to share quickly some of the lab, experiences, in their teaching. So the labs are taught by the TAs. Yeah. Priya, take it away.
Yes, so for the lab sessions, we teach the software arena simulation by Rockwell Automation, and we also teach a few of the companion tools. We teach the input analyzer, the output analyzer, the process analyzer. Also during lab sessions, we do homework help, we do exam review. We might cover some concepts that students are confused about during lecture. And sometimes we also just do troubleshooting. So the current lab structure is 1 hour per week, right? So we review statistical concepts, we cover the software, and then we provide help with homework or exams. And mostly the software is taught with a demonstration where the students follow along. They also have homework that are lab related, and there are lab related questions on the exam. And then one of the things that I found, in addition to just the demos, which can be very one directional, right? The instructor, the lab instructor is doing the demonstration, students are following along. One of the things that actually makes it much more powerful is if we do any troubleshooting live. Troubleshooting, you can learn a software by following along, but if you run into any unusual problems, you don't know how to fix it. So troubleshooting really is, I think, the most valuable use of the lab time. And then also I have a YouTube page that I started a few years ago, where I record videos of key concepts. They're short, typically 10 to 20 minutes. Students can go back and review what I've already covered. Now, during the pandemic, we did face some challenges going to a remote structure. One would think that because this is a software exclusive portion of the class, it would be easy to transition to remote lab. But actually, there was a lot of challenges. Students found that when you're looking at the WebEx or we use Zoom as our platform, when you're looking at the Zoom window, they found it really difficult to simultaneously work on their own models. So a lot of students ended up not following along. So one of the changes that I made was that I pre-recorded all of the demonstrations. And so then we switched. I had already previously found that troubleshooting during lab is a very useful use of the time. But post-pandemic, we made the schedule lag time solely for troubleshooting. And then also I implemented a peer-to-peer learning strategy where I selected students at random to present their models that they built along with the demonstration. There was no penalty if it was incomplete. There was no penalty if it was incorrect. It was just a way for them to explain their own model, which I think both fostered a sense of panic that they might get called on. So they actually, did the work before lab, but also, they, when they explain it, when you teach something, you just develop a deeper understanding of it. And then I would use their model to point out common mistakes, to point out areas of improvement, to point out where they had done things well. And then again, this troubleshooting live. So that's really how I transitioned to a remote lab. And so from both of these experiences, I find that fully remote learning is not ideal for lab sessions. You just lose a lot. You lose like real estate on your monitor space. Students also feel a little bit more inhibited to ask questions. And then when I'm teaching in person, you can sort of tell from people's body language or the expressions on their face if they're confused, if they're lost, if they're getting bored. And since I am on my computer with the software open, I don't see any visual feedback at all. So it is possible for the students to learn the software via demonstration on their own. In-person time is really best reserved for troubleshooting and covering in-depth concepts. Videos are helpful when they're shorter. We found that the longer videos just don't get watched, whereas the shorter videos are watched multiple times. And then this randomized student presentation really holds the students accountable for completing the work on time. It also helps them learn through teaching, but since there are no points attached to it, it doesn't impose a penalty. So it's a little less stressful that way. So that's what I found teaching the undergraduate lab. Nanshan, if you want to take over your insights for the graduate course.
Hi everyone. I am another TA. So my major takeaway is that I found lab is more than just learning the operation of a software, for example, Arena. It's more about applying knowledge learned in the class to understand the math stack behind this thing and develop the ability to build a model even without the software. So the next time when you use another software or you use some coding language like Simulink of MATLAB or SymPy from Python, you can still get your hands on very quickly. So with that in mind, I developed my lab session as follows. First, I will review concepts and theories in the class through slides, and then I switch to the Arena software and introduce some new aspect features in Arena. And then I will build some models from scratch to show students how is the approach. And we did learn quite a lot of interesting models like the electronic assembly system, coordinate system, and inventory system. And in last, I will have a Q&A for any question that students have for this class. Sometimes the lab will also be used as a homework review for exams. Yeah, that's all. Thanks.
Thank you very much. We are running behind time, so I'm not sure we can get to questions. Chiwei, do you the lab sessions and the videos they sound kind of familiar to your flipped classroom? Is that what it's about? Chiwei? Okay, maybe he's not there. So any quick question for Katie? Otherwise, we'll just have to postpone the question to the discussion session.